Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the acute tool sharpening system today. We've got lots more parts to make on this thing, and the part we're going to make today is called the setting block. It's a very, very interesting part. There's some really interesting features on this thing, and well, you're going to want to watch this, so let's go.
Sorry, that was a bit presumptuous. I don't know what you want to watch. Here's the piece we're going to be making today. It's called the setting block. We're going to take a look at what it does towards the end of the video, but for now let's focus on the very interesting shape of it. This will be quite a test of my ability to read drawings. There are 6 separate projections and 2 partial cutaways for all the features on this part. It's a lot to interpret. The kit supplies this piece of square bar stock that is already on dimension on 2 axes due to some high quality factory stock being supplied. So I just need to machine the other 2 ends that have what look like saw cuts of some sort. I'm going to machine one end by setting it up vertically in the vise like this. I'm going to get it mostly vertical with my square, and then I'm going to dial it in. You could also set this sideways and side mill it off the end of the vise. I chose not to do that because the piece is 25 millimeters high, so that's quite a lot of side milling surface, and I don't think I have an end mill that can do that. Plus, with side milling, you're going to get more end mill deflection on a piece this large, and so you're not going to end up with a perfectly square face on the end. The best way to ensure a perfectly square surface on the top then is going to be to indicate in the vertical surface. I've got my highest resolution indicator because it's not a lot of surface to indicate on, just a little bit over 25 millimeters, and I want to get this as vertical as I can. The shorter your surface is to indicate on, the higher resolution indicator you need because it's harder to detect error on a shorter distance. I'll use a brass drift to tap this thing vertical. This block is, I think, some sort of alignment or setup block for grinding operations, so I want it to be as accurate as I can possibly make it. So I'm going to be pulling out all the stops here on accuracy. For example, that deflection that I mentioned from side milling, 99% of the time it's not going to be enough to matter, and you see me do that all the time when I square in parts. But for this piece, we're doing it the quote-unquote most correct way. I'm going to repeat that footage of showing you the indicated in piece because there's something important to note here. When the indicator first starts moving, the needle jumps 5 or 6 tenths, but then after that it settles down and it only moves about 1/10 and a half. And that's because when the power feed on the head changes direction, the whole system loads up in a different way depending on whether it's moving up or down. So when reading a very high resolution indicator like that, you got to be aware of those types of things and only start paying attention to the needle after things have settled in their new travel direction. We're measuring very, very small amounts here, and these indicators can drive you a little bit crazy for that reason. But that looks good on this side. I also sanity checked it on the other side just to make sure, and everything is straight there as well. So I think we're ready to mill the top surface of this, and we'll end up with something extremely square. Measurements show that the piece is about 1.5 millimeters over length on this saw cut dimension, so I want to be able to ensure that I clean up both surfaces without going below 25 millimeters. To ensure that happens, I'm going to try to take the lightest possible cut I can that will clean up this surface, because it's hard to know ahead of time how much you're going to have to remove to clean up a saw cut. And if I don't get both sides cleaned up without going below 25 millimeters, well, then we're done. In this case, 0.5 millimeter was enough to clean that up, which leaves me a full millimeter on the other side, which should be plenty. With that side done, then I can flip it over and tap it in on the parallels because now we do have a square reference. And just to be sure, I indicated that in, and we are indeed extremely vertical, so that's looking good. Rinse and repeat on the other side then. I should have a full 1 millimeter to take off of this side, but I won't know for sure until I once again do the lightest possible cut that will clean up the surface. Then I have to take the part out and measure how much I actually have to remove from that point on. You can never trust a measurement that's done on a rough surface to know how much more material to remove. So you got to get it to a state where the piece is cleaned up on both ends, on both sides of the dimension that you're measuring, while still having enough to remove to get to your final dimension. With saw cuts, that really is the difference between success or failure oftentimes. And of course, you have to deburr all edges between all cuts and measurements. One thing I've learned over the years is that your milling skills improve dramatically when you get better on the bandsaw. The better and cleaner your bandsaw cuts are, The more on dimension they are, the easier it is to clean up parts and hit dimensions after the fact with the milling machine. Going in for what should be the final cut, I always go in with the end mill off and just make sure that it's not going to gouge the surface. That tells me if my tapping in was probably accurate, because the end mill should still be exactly on that surface since we haven't moved it from when we took the piece out of the vise and put it back in. Then I power the mill up and move over the piece and drop the cutter very, very slightly, and as soon as you start to touch that fine feed, you should hear it start cutting. And then you know that the end mill was in fact right where you left it, and you can get an accurate depth cut for your final pass from here. All those little moves like that, those little strategies to make sure that everything is where you think it is and that all of your previous steps have been accurate, I find really, really helps nail that dimension in the final product. All right, let's see how we did. Depending on how you hold your nose, yep, that's definitely dead nuts, or at least within 10 microns. Of course, according to the guessometers, and the final digit on any digital tool is always a little bit of a fiction. We'd need a high quality metric micrometer to know for sure, but I think we can call that extremely good. There's something very, very satisfying about a cube that is as perfect as you can make it. This is within 10 microns of being a perfect 25 millimeter cube. Of course, very high quality factory stock did most of the work here. All I did is face the ends, but I'll take credit for the whole cube anyway. Next up, we have to make a 45-degree angle cut on one of the corners. This also needs to be as accurate as I can get it. I'm going to start by once again setting it approximately with my little square. Now, even though this square is very, very accurate, setting things by feel, just pushing things up against other things, has limits on how accurate that will ever be. In this case, you'll see the error that's created by doing it that way. Most of the time, again, that's good enough, but if you're trying to get a really, really accurate angle on a piece, then you're going to need to find a way to indicate it. What I've decided to do for this piece is clamp my little angle square on the surface, and that's going to give me a nice, clean vertical edge upon which I can easily indicate without having to do a bunch of trigonometry. After that initial setup, you can see that just doing it by feel up against that 45-degree angle is out by about 0.02. Sorry, the framing cuts off the indicator, but it's at 0 at the top, and then when I get to the bottom, you can see it's on about +2. So that's the error that we got just by doing it by feel, by setting the piece up against a reference. Once again, you cannot beat indicating for accuracy. Now I've got my brass drift down under the far corner, and I can tap it from under there because I need to tilt it towards the camera a little bit at the top. Luckily for you, I noticed the framing error, and here is a better shot of the final alignment. My cinematographer has been temporarily suspended from duty and told to go file some cubes. Now, just to be sure, I'll bring in the tense indicator like we did when setting it up vertically. I got lazy and used the half-thou indicator to get it set up initially, but now we'll get the real truth teller in here. And actually, it looks like we did really well with that. Once again, understanding that when the head changes direction, there's going to be a half-thou needle jump, but then once it's settled into the new orientation, it's only moving about 1/10, maybe even less. So that's really, really good. Next, I need a reference from the front edge of this part, so I've got my Heimer edge finder brought in for this. This thing is great, even though it's indicated in imperial, the units on it don't actually matter, so it's great for these metric machining projects. I find that front edge, zero my y-axis there. Now, for the depth of cut, I need to find the top edge of the part. This is probably the least accurate thing you'll see me do on this part, but I really don't have a better way to do it. I'm coming down onto a feeler gauge of a known thickness, and once that feeler gauge is measuring correctly, which is to say light drag, then I know the end mill is exactly that amount above the surface, then I can lower it by that amount on the quill DRO and zero it. Now, the reason I say this method is imperfect is because that top corner of the part might have a little bit of a chamfer on it because it's been deburred. I intentionally did very light deburrs on all of these cuts to minimize this amount of error, but just be aware that there is some potential error there. We're really trying to measure some imaginary perfect corner on that top edge that doesn't exist. You can't not deburr it because then you're just measuring a burr, which is usually even worse. The drawing gives a final measurement of 10.5 millimeters for one edge of this final part to the corner of the cube. So I had to do a little bit of trigonometry and calculate that I need a drop of 6.83 millimeters straight down from the corner to create that feature. Next, the drawing calls for that same feature on an adjacent corner, but on the opposite side of the part. So I rotate it 90 degrees and flip it 180. and then do the same feature on the front of the part once again. This is a little bit mind-bending and exactly the kind of spatial reasoning that I always screw up in the machine shop, so I brought in the isometric drawing once again to really make sure that I'm doing these two features in the right way. It's a kind of a tricky relationship. As you may have guessed, for most of these cuts on this cube, the parallels in there are just decorative. Nothing is being tapped down on there. I'm relying on the piece being held in the vice jaws and being indicated incorrectly. For that reason, I'm also taking fairly light cuts because I'm relying on the friction of the jaws to hold the piece in place. But 1mm cuts in this free machining steel worked out just fine. That is looking really, really good. A little bit of deburring and cleanup. Let's see how we did on dimension. Wow, look at that. Hang on, just gotta wiggle it till I see the number that I like. Yep, perfect dimension. Compare to the isometric one more time, and I think I actually did that correctly. Look at that. Those two weird half 45-degree shapes seem to be in the correct relationship to each other. Next up, we need a 2mm slot, so for that I'm going to need a 2mm slitting saw, which I happen to have, amazingly. Fun fact, all of my slitting saws are actually metric, because they were all donated by, I think, a European viewer at some point. The dimension of a slitting saw usually doesn't matter very much, but in this case it does, because the drawing specifies a 2mm slot. Unfortunately, this saw is not in very good shape. So I'm going to do a test cut with it. These saws are all used and of unknown sharpness, and this one did not feel super sharp. It's also got a red dot on one tooth, which suggests a bad tooth in that spot. And I don't want to subject my main workpiece to this if it's just going to make a mess. So I've grabbed a piece of scrap and let's see what happens. But actually, that seems to be cutting just fine. I'm running it at 365 RPM, nice slow feed, about 1/4 millimeter per second, feeding by hand, but ballpark, that's about what I was doing. And that made a really nice slot, I gotta say. Really nothing to complain about there. So I think this saw is okay. The drawing specifies the distance to the top edge of the slot, which I really like because that's a lot easier to line up. Drawings often give you the center line of the slot, and then you have to remember to do the math on the thickness of the slitting saw blade, which I always forget, and all my slots end up half a saw blade off, but this one was easy to set up. Then for depth, I feed in very, very slowly until I just hear the saw blade contact the work. This you do have to do with the tool spinning, not like you saw me do with the feeler gauge and the end mill, because slitting saws always have runout in them, they're never manufactured perfectly. So if you measure with the saw stationary, your measurement is going to be too high or too low depending on where in the runout of the saw it happens to be sitting when you do your touch off. Touching off with the saw spinning cancels out that error. Quick sidebar on slitting saw geometry, because I get this question a lot from woodworkers. Slitting saws are a machining cutter. They do not have a set on the tooth, so they cut at the exact kerf width of the saw. Each tooth has an internal geometry of a grooving tool, say on the lathe, so each tooth clears its own chip and has its own clearance built into it, so the saw cuts exactly on dimension with no set required on the teeth. Tooth set on woodworking saws is just an inexpensive way to avoid having to give each tooth sophisticated geometry. But as you can see, this is cutting pretty well once again. I'm, again, as I always say with slitting saws, doing the full 8mm depth of cut in one pass. The best advice I ever got for slitting saws was to always do the full depth in one cut. They clear chips better, and they cool better, and they cut better when doing a full depth of cut all at once. This was going fine until about 2/3 of the way through the cut, and I started to get a clunking noise. Do you hear that? Like an intermittent clunk? So probably one of those teeth has gone dull, maybe more than one. Maybe that one with the red dot on it. Who can say? Some previous machinist put a red dot on this saw for some reason, but I got away with that. I slowed down my rate of feed a little bit and nursed it through. That might be the last cut that saw ever does in steel. Probably still okay for brass or something like that, but got away with it for one last cut. It was one day away from retirement. I made it do one last mission, and it did a heck of a job. That is a beautiful, beautiful slot, and would make a very nice Rebel base. I did have a moment of panic when I compared it to the isometric and saw that my slot was mirrored to the wrong side, which again is the exact type of spatial reasoning error that I always make, but then realized, oh, all is well. Next up, we need some holes. So I've got it up against the Heimer once again to find this corner, which is where the drawing references this hole. And we need to do an M4 threaded hole just through into the slot. I'm going to pack the slot full of some shim material because when we're drilling into it, it may tend to deflect and compress. Typically, when you've got a slot and a hole that intersect, you do the hole first for exactly this reason, but the build notes specifically say to do the hole after the slot, so there's probably a good reason for that. Perhaps to make sure that you get the threaded hole to exactly the correct depth, I'm not sure, but I probably would have done it the other way in hindsight. I am going to have to bottom tap this because we want the threads to go right down into the slot according to the drawing, and there's no way I'm going to be able to do that with a taper tap into such a narrow slot. Rolling the part over one more time and indicating on this side we need a hole centered on this edge. The drawing actually does not specify a depth for this hole, which is a little bit annoying, so I had to kind of deduce it from its relationship to other parts. This hole is apparently for a work stop pin that's on one of the other linkages in the mechanism, and the length of that pin was 3 millimeters. I also took a measurement off the drawing to sanity check that. Got to be a little cautious about doing that though, because as in this case, even though the drawings are 1-to-1 scale, they are not printed 1-to-1. The printing operation that made these spiral-bound drawing books has scaled the drawings down to 0.92. So I took a measurement off the drawing and then had to scale it up by 8%. Next, we need a second hole right on center for a recessed magnet. Again, no dimensions provided for this hole, but the drawings strongly suggest the magnet is supposed to sit flush inside this hole. So I took measurements off the magnet that's supplied in the kit to get this dimension. Let's see if I got it deep enough. I went a little bit conservative on the depth just to make sure I don't go too far. And yeah, sure enough, that's a little too shallow. Now I just got to get that magnet out of there so I can drill the hole a little deeper. Nope. 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 Nope, not waiting. Nope. Ooh, what about? Nope. Okay, but surely. Nope. Ah. But. Nope. Maybe. And. Nope. Aha. This. Nope. But. Nope. Yes. Turns out you just need a big enough stack of much stronger magnets to get a small magnet out of a block of steel. I was on the verge of resigning myself to sanding that magnet down flush. But I did indeed manage to get it out, drill the hole a little deeper, and now we're nice and flush right there. That looks good. By the by, if you do ever need to shorten a magnet, don't try to mill it, you need to sand it or grind it. Neodymium magnets are very, very hard, typically about 60 Rockwell C, so you'll chew up your end mills trying to machine them. And they tend to shatter. Now I know you're wondering what this block is for. Let me show you it in context on the table that we built earlier. There. See? Oh, that's still confusing. Here, let me arrange it as shown in the photograph of the entire tool sharpening system. I think then it'll make more sense. So if I just, there we go. Yeah. Right there. Perfect. There. See? That's the setting block. Well, that was a really interesting part to make. It was really fun to try and make something like this as accurately as I possibly can with so many interesting angles and other features. I really, really enjoyed this little piece, and it's really neat looking. I still have no idea what it's for, but we're going to find out by the end of this project, I'm sure. Thank you so much for watching. Thanks to my patrons for making all of this content possible, and I will see you next time.